Okay, so time to restart, and we have a hard wall boundary at 7, so keep me on time. Uh, no. We'll stop in time so that there are questions. Okay, so this set of two more courses will be a little bit different than the introduction course, because now I will specialize to something which is studying in particular fermions, but more generally quantum systems in one dimension. And I'm sorry, I will start again by a couple of slides, because I think it's important again to tell you, very short number of slides, to tell you why bother about one dimension. The main point, as we will see later, is that with cold atoms it's very nice and one can realize many one-dimensional systems. But I wanted to give a more general motivation of why look, not loot, but look at reduced dimensionality. One motivation is practical, again, in the same spirit than this morning, looking at materials or thinking about materials. Again, people are miniaturizing everything. Here is an old data set of transistor as a function of time, and of course you can imagine that if this thing goes up, then the size of the object has to go down in the same way, which means that let's say material way to understand systems has gone from the idea that you were looking at big chunk of material, bulk material, to something where you have to worry about systems which have either essentially zero dimension, or if you want to use wires to connect these things, then the dimension will be so reduced that you might have to worry about objects which will be one-dimensional. You know, even a copper wire in the wall is so large compared to the interparticle distance that they are three-dimensional objects, even if for us macroscopically they are one-dimensional object. Microscopically, for the electrons, they live in the 3D world. But you can confine things, and we'll come back to that, so much that you have to worry about this one-dimensional aspect. So that's a kind of, I would say, practical motivation. But there is an even stronger motivation, is that people understood that there is a lot of fun that happens at the edge of even bulk materials. One of the first person to have discovered this is Bert Alprin, and it was in the context of the so-called quantum Hall effect, where people take a slab of metal and put it under a strong magnetic field, and then you get Landau levels, which is discrete energy levels inside the bulk. So the bulk is relatively boring, it's an insulator, but because you have the edge of the material, the energy levels, they go up at the edge. And so when the edge crosses the side of the sample, the edge can have very different properties than the boring bulk, which is in the middle. And this is something that people have investigated a lot very recently with new materials called topological insulators. There are things which are called spin-Hall effect and so on, which is that you can have a material which is completely boring in the middle, let's say an insulator, but you have modes which only exist at the edge of the material, which can carry spin, charge, and so on. And of course, this mode living at the edge of a 2D sample will be one-dimensional. So there is a lot of also a fun effect that people have discovered there, and that needs to be explored. I can give you, among all this reduced dimensionality system, of course I have a special fondness for one-dimensional systems, and I'll try to explain a little bit more why. But let me give you an old reason, which was given by Freeman Dyson in 1967, and you can really see from the text of this that this was another time, where he says, okay, working on one-dimensional problem is merely that they are fun. So, you know, they are the source of beautiful things. And he says that, okay, a man grows stale if he works all the time on the insoluble, and a trip to the beautiful work of one dimension will refresh his imagination better than a dose of LSD. So I'm not promoting one-dimensional system as a substitute to LSD, but I think the message is that, as you will see, there is beautiful and fun physics to get there, and I think it's a good reason. Now, before we move to writing things, one dimension is especially interesting because it's the dimension in which you're the further away from the type of physics we discussed this morning and that you would expect in high dimension. Again, here you essentially move in a two-dimensional world. I mean, you're three-dimensional because you have to stay on the carpet. Your motion, your vertical motion is zero, so you're two-dimensional objects. And you have an infinite repulsion between you. But nevertheless, you behave as individual particles. You behave as individual objects. If one of you wants to move in the crowd, you just push a little bit the people in the crowd and you just move as an individual particle. So this is the physics of Fermi liquids that we were discussing, these interacting particles. You can have as strong interaction you want with the other particle, they just push a little bit the crowd, and then they can move with a renormalized mass. So this is the type of physics we expect even in two dimensions. Now, in one dimension, if you have queued to see a movie or whatever, you know that no individual motion is possible. You can only move if the whole file moves. And same thing if you're trapped in traffic jams. I think some of you coming to Les Houches experienced that in Geneva. If you want to be behaving as an individual particle here, you need an extra dimension. You need to be able to pass and move. Otherwise, you move as well or as badly as the whole collective behavior of the system. So there is a kind of collectivization of excitations in one dimension. Well, it has a more fancy name. It's called bosonization, but I'll come back to this. And so essentially, you can contrast this physics with this physics. And that's something which is very important because the fact that you lose the individual excitation will have deep consequence on the physics. On the more technical level, 1D, the more you lower the dimension, the more fluctuations there is, either thermal or quantum. And most of the tools that we have as theorists to solve problems, they are based on some mean field approximation. You assume that there is an order, for example, superfluid order, or I have a wave function, it has an amplitude, it has the phase, and if the phase is locked, oh, that's great, it's a superfluid. And then you say there are small oscillations or perturbation on the top of this. And we've built a whole theoretical machinery which works around this. Well, in 1D, forget it, there is a theorem which is called the Orenburg-Wagner theorem, which says you cannot break a continuous symmetry. So all this goes to the garbage can. Mean field theory, garbage can. So you lose most of your theoretical tools and you have to do something to try to understand what to do. So this is a fun world with very weird properties, and it's something which has been explored since a long time. I mean, it started, let's say, in the 50s or the 60s, and there are three urban legends about 1D that I would like to blast off in these lectures. First, and we already heard this in previous lectures, oh, I write it in 1D because it's easy. Yes, I do the same, so I plead guilty. But 1D physics is not necessarily just a toy model to understand higher dimensional systems. Actually, very often it's very different from higher dimensional systems. So that's something one needs to show you, and I'll do it. What is more worrying is people who say, you know, 1D is only for theorists. It's kind of intellectual dreams and whatever. It doesn't exist in nature, and cold atoms have blasted this away. Not only cold atoms, but in particular cold atoms, and I will try to show this to you. And the last thing I would like to blast off, but it will not be done in the first lecture, because in the first lecture I will tell you what we understand. But the idea is, 1D at the end, everybody understands everything there, and so it's not interesting, let's move to something else. And of course, a field is only interesting if there are challenges that remain, and I'll try also to show you in the last lecture tomorrow that there are things which are still very much resisting the efforts, even in 1D. So this is simply completely and totally wrong. Okay, I will give a set of references. They are in increasing order of complexity here. This is again lecture notes of a school that you can look at, which are relatively simple. Then there is a book. I'll leave a copy. I'll give a copy to the library here in Les Houches. This contains everything you want to know about 1D and probably everything you don't want to know about 1D. This was written in 2004, so it's interesting that this was written just when cold atoms were exploding. So the book is semi-obsolete, and I'm working on a second edition, so I'll try to compensate for the things which are missing in the book, but at least for the machinery, everything is there. Then we wrote some more recent and up-to-date review in modern physics and so on. So depending on what is your desire to go deep into 1D in the 1D world, then you can look at these various references. Okay, so enough for the slides. Let's now go back to the trying to do something directly about the 1D world. And of course, before entering the 1D world, so I'll try to write on the tablet and then can give you the transcript of the writing, which should help. So before we go to the 1D world, I have to make a couple of reminders of, let's say, high dimensional fermions. So of course I will do it since you will get a more detailed lecture on oops, not very fantastic, but okay, good enough. I'll move it later. Okay, so first it's free fermions, and I'm sure you all know the basics for free fermions, but let me remind it to you. So I'll try as much as I can to avoid using second quantization, even if I'm sure many of you know it. I'll stick to first quantization. Of course, it's more convenient when interaction will be put to switch to the formalism of second quantization, but for free fermions, doesn't matter. So if I have, let's say, free fermions, I have an Hamiltonian, which is sum over I equal 1 to n. If I have n particle, pi square over 2m. This is really free fermions in the vacuum. And then you know what happens. The eigenstates have an energy, are plane waves. They have an energy, and I do h bar equals 0, which is k square over 2m. And then because fermions have the Pauli principle, you cannot occupy all the eigenstates more than one. For the moment, I forget the spin. If you're in a box, let's say, with periodic boundary conditions, so if I take a box with periodic boundary condition, which is also known as a donut, yeah, some people said that for some of the conditions, Haldane did a lot of work, and so it's called Duncan donut. No, okay, I will not do this joke. Anyway, so k is quantized. So for example, kx is 2 pi over lx times a certain number nx. And so you have to occupy the states, each at most by one fermion. So essentially what you have is an energy dispersion here, epsilon, and I'll draw it in 1D even if I am supposed to be in higher dimension, Gesundheit. And you get the values of k which are allowed. And of course, now you start to occupy this value of k to put the fermions you have. And at the end of the day, you end up at a certain energy level here, which people call the Fermi energy, which is the energy of, let's say, the last occupied state. This difference in energy scales to 0 when the size of the system go to infinity. So we won't go into subtlety of how to define the Fermi level. But the point which I was making this morning is that this energy can be extremely large. In solids, it's typically of the order of 1 electron volt, so it's 12,000 Kelvin. And of course, you see that if you look at temperatures which are much lower than this Fermi energy, essentially, this thing is direct manifestation of the quantum effects in the system. If the temperature is so large that you can thermally excite these guys out of their state, then you don't make the difference between classical particles and quantum particles. In cold atoms, the Fermi energy, of course, scaled down by several orders of magnitude. It goes down in the hundredth of nanokelvin, and this is exactly what we were discussing. Now the temperature, which is itself, let's say, or 100 or 1,000 of nanokelvin, and the temperature itself is now very low, but not that low compared to the Fermi energy. But nevertheless, the feeling of the particle is the same. So if you plot, for example, the momentum distribution of free fermions, then this is what you all know. So if I plot the number of particles with momentum k as a function of k, then at t equals 0, this is a box which stops at kf. Let me take a spherical Fermi surface, so really my free fermions. And here the occupation is 1. Here the occupation is, of course, 0. Now, if you're at finite temperature, this is the Fermi function. So temperature broadens this thing a little bit. So this is just what I want to say about free fermions. Of course, if you're not free, if you're on a lattice, for example, so if you have in 1D fermions which could hop from one side of the lattice to the next by this tunneling element that we wrote. So if I have an Hamiltonian which is minus t sum over I, let me write it in 1D, I plus 1 I. Then you know how to solve. You go to Fourier space. You make a state which is a linear superposition of this state with Fourier components. So you will write states which are k is the sum over I of exponential of ik ri times I. And I should call it j because there are too many i's in this equation. One is the complex number, the other was the site. And so if you use this, it's easy to show that this Hamiltonian becomes the sum over k of something I will call epsilon k times k, and epsilon k is simply minus 2t cosine k. I'm not going in details because I'm sure Hélène will do this in her course in great detail. So essentially, the fact that k-states are good eigenstates is the consequence of the discrete translational invariance of the problem. So it's quite logical. You see that compared to my parabola, the dispersion here has various things which are different. The first one, it's not a parabola, it's a cosine. I should, if I want it to be clean, I should put here a length, which is a, which is the lattice spacing here, the distance between these sides. And I should say also that all values of k are not allowed. So k is still quantized as before, but now k is restricted to be in an interval which is called the first Brillouin zone, which is k can only describe the values between minus pi over a to pi over a, or any interval of periodicity to pi over a. And again, I don't want to go too much in details unless you really want to know, because I'm sure that Hélène will do, given the title of her course, will do this for you. You can check, of course, that if you count the interval is of length 2 pi over a, k is quantized as 2 pi divided by L times n. So the number of independent k value that you have is exactly n, the number of sites. And just tell that you didn't create or destroy information by doing your Fourier transform. You start from n independent state in your basis, each site, and when you go to Fourier space, you must have n independent state in your basis, and you can recover this there. The point I want to make is that now the dispersion is something which is like this, going between minus pi over a, and of course you see that if k is very low, which means in a way if k is very low, your wave function is varying very slowly, so it doesn't realize that there is a discrete lattice, it sees a continuum, and then you should recover the parabola. And indeed, when you expand the cosine close to the bottom, the cosine is a constant minus k square, and you find back the parabola. So again, I'm going a little bit fast on the free Fermion case, but I think this is all what I want to say. The thing which is important is that now, of course, the energy is something which is going between minus 2t and plus 2t. So contrarily to the parabola, it's not bounded, it's bounded from the top here. So this second model here is called the tight binding model. And this is a model which is widely used to describe solids because, of course, you would say the electron spends a lot of time around one particular side, so you don't care. You say it has a wave function, and then it can just go from one side to the next. And as we were discussing this morning, this is also an excellent model for cold atoms, because if you have the periodic potential and it's deep, you can say my atom is spending time at the bottom of one well, then tunneling to the next well, and so on and so forth. So this is an excellent model to describe this type of thing. So before I move forward, is there some questions on this free electron picture? No, it's quite okay. Okay, now I want just to introduce a final quantity, which is what is the probability to measure an electron or a particle with a momentum k and the energy E. So what is it? I have three particles, and I'm asking you, I try to create an excitation in the system which has the momentum k and the energy E. What is the probability? Yeah, it's a delta function, of course, because the only way I can do this, let's plot it as a function of E, is by saying, okay, let me add one particle here. Let's forget that it's occupied for the moment. I add a particle here, and then, of course, this particle, if I know the momentum, I know the energy. It's epsilon of k. So this is a delta function. This is here, a delta function, delta of E minus epsilon k. For people who already know a little bit Green's function, this is the imaginary part of the single particle Green's function, which is sometimes also referred to as the spectral function, and it tells you how you can create single particle excitations by adding, or if you have a Fermi C, by removing excitation, because I can do the same thing here. If I remove one particle here, I've created a hole in the Fermi C, but again, its energy is perfectly related to its momentum. Okay, so that's three particles. Now, let me give you the crash course, something which I will call Fermi liquid 101. So it's not even a description of Fermi liquids, but that's... Now I add interactions. How are these results modified? So the naive thing would be to say, if I add an interaction U, each particle can exchange an energy of order U with the other. Whether the interaction is long range, short range, it doesn't matter at that stage. So you could imagine that the interaction is playing a little bit the same role than a temperature. This particle which was occupied with probability, this state which was occupied with probability 1, this state is empty. But now if I have interaction, it means I have a kind of uncertainty on the energy of each particle. And this energy is of the order of U, the order of the interaction. So you would naively say, oh, I have a broadening of the Fermi step here by like a temperature of order U. So the naive answer, so if I add an interaction U, the naive answer is to say, oh, my n of k should be something which, instead of the perfect box, is something like this, where this has a size which is of the order of U. Well, the particle at the bottom, they are not really affected, because even if they change their energy by a quantity of order U, the Pauli principle is still blocking them. So the only one which can be affected are the one where they can go from this state to an empty state. And that's a very reasonable assumption. except it's completely wrong. And this was what Landau showed. This is Landau Fermi liquid theory. The right answer, so Landau Fermi liquid theory, is that the n of k, so actually it starts good. So it starts as if indeed there was a kind of broadening of size u, but then remember I told you it's like free particles. Free particles, they have a jump at kf. So you preserve the jump. So instead of having the smooth thing, you just get something, a jump, and then again a smooth thing. So you get a jump, but the amplitude of the jump is reduced. It's reduced, and now it has a height which people call z traditionally, which is usually smaller than 1. But the main message is that the n of k still has a jump, even in presence of interaction. Now if I plot on the same diagram the spectral function, so the probability to find an excitation of momentum k and energy E, you would say the same thing. Before I had a delta function. This is k1, for example. So this was for k equal k1. Now I can exchange energy. So this should be becoming a Broden Lorentzian or a Gaussian or whatever of width u. That's a very natural assumption. And it's roughly correct. You get something which is a potato here, which has a certain width. The point is that by a combination of Pauli principle and so on, you find that the width is becoming more and more narrow. So I'm sorry, I cannot draw it with scale, but the peaks are becoming higher, of course, to conserve the spectral weight. The peaks are becoming more narrow. So this is the width W1, this is the width W2. So this would be centered at another energy. So this would correspond to another k equal k2, closer to the Fermi level. And the more you go close to the Fermi level, the less the width become. And you can show that the width is negligible compared to the position of the peak. In other words, you recover free particles. The width is negligible compared to delta E, where delta E is the energy minus EF. Now, if you think in Fourier transform, a finite width in energy is a lifetime for the wave function. It means that instead of having a wave function psi of t, which is just exponential of I delta E times t, you get also something which is exponential of minus absolute value of t over a certain tau. When you do the Fourier transform of this, you find not a delta function peak, but you find a Lorentzian of width 1 over tau. So if I do the Fourier transform of this, you would find that this is centered around delta E, and this has a width, this has a Lorentzian profile with a width which is 1 over tau. And now what I'm saying is that the lifetime here is becoming very large compared to delta E. Why is it important? Because delta E is giving you the oscillations of the wave function. So it gives you the natural scale. 1 over delta E is the natural scale. So if you want to see and determine delta E with accuracy, you need a lifetime much larger than the many oscillations. So what I'm telling you is that the wave function is really behaving as an oscillatory function with the energy delta E and only decaying extremely slowly. And the more you go to the Fermi level, the longer lived are the excitations, which is totally contradictory to intuition. You would imagine that the width is always u, the order of the interaction. So again, I don't want to insist too much on this, but I just want to tell you that this is what you expect in high dimension. And in a way, you can forget about these complications and keep the image of free particles. So it's not exactly free particles, but it's something which is as close to free particles as you can imagine. And if you don't believe me, and you should not believe me, so this is what I just said, that you get, this is free electrons, this is free particles, this is the delta function in the spectral function, this is what you get for interacting particles, and this is what you would get for two different values of k, one far from the Fermi level, one much closer to the Fermi level. And you can use a technique which is known as photoemission, where you inject photons on a solid and they kick out one particle, and there is a corresponding method in cold atoms that we can discuss. It's RF spectroscopy coupled to a measure of the n of k. And doing this, you can measure this probability of finding an excitation with a given momentum and a given energy. Why given energy? Because if you send a photon with a given energy, and if you measure the energy of the electron which goes out, you know the energy of the electron in the solid. And by putting your detector at the right place, you measure the momentum of the excitation. So this is something you can measure. Yeah, just. No, so there is very little assumptions on the interaction itself for the Fermi liquid theory, and that's one of the difficulties. In a way, you never know if it works or if it doesn't work. In 1D, it always fails, even if the interaction is super small. In more than 1D, it very often completely works. So the fact that you get these things, you get these properties, they are linked to the fact that the possibility of having excitations is essentially blocked more and more by the Pauli principle when your energy is getting closer to the Fermi level. So this is really a phase space argument. So I'm not sure I understood your question. Ah, that's a very good question. Yes. So you're absolutely correct. It's far from obvious. There is something called the Luttinger Theorem, which shows, and it was proven in the physics sense, not in the mathematical sense, that actually Kf is not changed. And you're right, it's not obvious. Actually, what the theorem proves for more complicated Fermi surface, that the volume of the Fermi surface cannot change. And it's non-trivial. I mean, you really need to work it out. And your assumption is perfectly correct. A priori, I put interaction, I could change Kf. And actually now, we know systems where interaction would lead to a spontaneous deformation of the Fermi surface, so which would violate this Luttinger theorem. So you're perfectly right. There are systems for which this happens, but for most of the system, it doesn't happen. So the density of state will change because you're renormalizing the mass. And what counts, in a way, is what happens in a small sliver very close to the Fermi level. And again, this is because in a solid, people have to deal with excitations at energy which has to be small compared to this 12,000 Kelvin that we were discussing. If your temperature is only 1/10 of the Fermi level, of the Fermi energy, then a lot of other processes need to be taken into account. This is not free particles, but this is getting closer and closer and closer to free particles. If you take into account the modification of the mass due to interaction, absolutely. Yeah. Let me show you the results before moving. Okay, I'm not discussing this, just to show you that you can do it even for Fermi surface, which are complicated. But here is experiments that were done on some surface of molybdenum, and you see very clearly, this is measurement of the spectral function for various momenta. And you see that when you go closer and closer to the Fermi energy, which is the 0 here, the peaks get narrower and narrower. And you can even check that the width that remains here is entirely controlled by the temperature. Which means if you were sitting exactly at energy 0, the only width you would see for this peak is the thermal width. So if the experiment could be done at lower temperature, the peak would become even more and more narrow. And same thing for the n of k. You see here the measurement of the n of k. So actually it's n of e, but let's not go into the detail here. And this is the broadening which is due to which is measured at various temperature. And you see very clearly that the more you lower the temperature, the more this would go to a step function with a finite discontinuity, and that the broadening is absolutely not linked to a finite width due to interaction. So just to show you that these things can be measured in nature. So this is not something which is pure speculation, but something which now is very well established experimentally. But the net result is that you can forget about the interactions in higher dimension, and you can really think that you get free particles in first approximation. So this is very good because everything we will do in 1D, you can compare to free particles. And then you're comparing to Fermi liquids. Okay? So now let's enter the 1D world. So let's go on the other side of the mirror and look at 1D quantum. Systems. And the first question we need to address is what does 1D mean? Because, okay, we live in a, maybe in an 11-dimensional world, I don't know, but at least for practicalities for us, in a 3-dimensional world. So what does it mean I'm looking at a 1D material? Of course, as a theorist, I can always write things, but does it exist? And the answer is 1D would never exist without quantum mechanics. So let's look at a very simple problem to try to understand what is going on, where I would look at a system which is between walls of infinite height, and this size of the system here I will call A. And the system is very long, and I will call this L along one direction. So this is kind of a trench, and now I want to put particle inside that trench and look at their wave function. So this is very easy. I have free particles, so let's do it in 2D just for simplicity. So my Hamiltonian is, let's call this X, and this Y. Let's do it in the right direction. Otherwise, so I have px squared over 2m plus py squared over 2m. So I know that the energy epsilon depends on two wave vectors, kx, ky. So it will be kx squared over 2m plus ky squared over 2m. But now I have to quantize. So let's say L is very long, so it doesn't really matter what I take as quantization. I can put a box if you want. So I would say that kx is something which is of the form pi over Lx times an integer nx, because the wave function, it's clearer if I do it on ky, is pi over a times ny. Well, let's call it ly, that will be simpler. Ly and ly. And because my wave function is something which is sine ky y, I want the wave function to be 0 on 0, and I want the wave function to be 0 at L, so this gives me this quantization condition. It's slightly different from the periodic boundary condition quantization, but that's essentially not very important. But what is important is that Ly is small, while Lx is very large. Now, if I look at what are my energies, I can classify by values of ny. So let's do it. So first I have ny equal 1. Then my energy of kx, ky is something which is 1 over 2m times ky is pi over ly, which is a large number, relatively large number, square, plus kx square. Now, if Lx is very large, I can consider Kx as essentially a continuous variable. Okay? Now, if I take Ny equal 2, then I would get the same thing, but I would get here 4 pi square over Ly square plus kx square. So I could plot the energy under this form, kx, ky, and I could plot it only as a function of kx, but I have eigenstates that correspond to different values of ky. So this is ny equal 1, ny equal 2, ny equal 3, and so on. The scale is not correct. It goes as the square, sorry. It's kx, sorry. Thank you. It's kx. So again, kx is quantized itself, but it's quantized in a very, very smooth and continuous way because Lx is very large. Now, it means that if I'm starting to fill my system, well, I will start putting my fermions here, 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 and then let's say I have enough. So if I have enough, you see that now I have enough state to accommodate all my fermions. Then you see what will happen. It means that I will have only these states that are filled. So my Fermi level will be here. Okay. So only the quantum number ny equal 1 is present. Now if I have an interaction, I can do whatever I want. I can scatter my particle in any state. But if I want to take one particle here and bring it here, I have to pay a finite energy. So it means this process, they will be strongly discouraged. So unless my interaction is of the order of this difference of energy, or my temperature is of the order of this difference of energy, what I will do, I will scatter the particle in this band, but I won't go explore the higher band. It's like what you got this morning when you say I get 2 levels, I consider that they are the only one involved, and the other, they are too far, they don't contribute. So I'm just saying if I get small interactions, an interaction typically take 2 particles with momentum k1 and k2 and scatter them to state k3 plus k4 so that it conserves momentum. So I can change the momentum. But then, if I want to conserve the energy, I would need to provide this energy. So this energy can be virtually provided by the interaction. But if U is small, so if U is much smaller than, let's call it here, delta E. Well, in first approximation, you cannot change the quantum number ny. In other words, the only quantum number that can change in the collision is the quantum number kx. So your wave function is 2-dimensional or 3-dimensional. It has a finite extension, but some quantum numbers are completely frozen. And then the only quantum number changing is a 1-dimensional object. So for all practical purposes, I can write an effective 1-dimensional Hamiltonian which describes the scattering of this only degree of freedom which is affected by the interaction, which is kx. So again, the physics is 3-dimensional or 2-dimensional, but at the end of the day, the only quantum number or quantum numbers, because you get one for each particle that I'm interested in monitoring, is a 1-dimensional object. And therefore, my Hamiltonian is purely 1-dimensional. So again, without quantum mechanics, without quantization of the wave function in the transverse direction, this would simply not occur. Also in practice, you cannot make a tube narrow enough compared to the width of an atom. You know, atoms, they would avoid very easily in any confining potential that you can put. But if their wave function has a certain extension, they are trapped. You need to excite them to the next level, and if this level is inaccessible in energy, it means you can stick to a 1-dimensional system. It also means that if you try to crank up too much the interaction, you will leave the 1-dimensional world in practice, because now you would get enough energy to get excited. So you have to find the right compromise if you want to make a system, because if you crank up too much the interaction, you have to worry about the higher bands. You have to worry about the higher degrees of freedom. But so in practice, what a one-dimensional system means, it means a system in which you manage to make the transverse dimension small enough that this energy has been pushed far enough from the relevant energy scale that you have in your problem that you can safely ignore it. And if you have understood this, you have understood most of the things that I will say. So is it okay, or? Okay. There is another way to get a one-dimensional system, but it's a little bit cheating, but I will tell it to you anyway. And let me take an example, which is the following. Let me consider a system which is made of many 1D chains like this. And I say I have possibility for the particle to jump from one chain to the next chain. So we determined before that if I have, for example, a system here with T, let me call it T parallel, then the energy was minus 2T parallel cosine K parallel A. Well, if I put here a T perp, and I say I can tunnel in the perpendicular direction, I will add minus 2T perp cosine K perp B, if you want. So this is the energy that you get if you have two-dimensional movement. So essentially, your particle can hop here, then hop there, then continue there, then continue there, and so on. Okay, so this is my energy, and this is describing a two-dimensional system. Now, how can I make this two-dimensional system 1D? Well, if I have a finite temperature, then I have to compare this energy to temperature, because I want the system to stay coherent. So there are two cases. Again, let me assume that T parallel is much greater than T perp. In other words, the chains are very weakly coupled. The tunneling from one chain to another is very small. I can put myself in a situation where I could have T parallel is much greater than the temperature, which is much greater than T perp, if I choose well my temperature. If I am in a situation like this, it means that every particle will suffer many thermal scattering before it can jump, and then many thermal scattering before it can jump back. In other words, chains will be completely decoupled because they cannot be coupled by a coherent wave function. So I will be in the 1D regime. So in this regime of temperature, this will be effectively 1D. And you see that there something weird will happen, is that if I look as a function of temperature, I will have a certain temperature T star, above which my system is effectively 1D, namely I can ignore the coupling between the chains, but if I lower the temperature, or if I raise T perp, the system will cross over to a 2D regime. So you have a phenomenon which people call dimensional crossover, where by changing one parameter in the system, you can have either a system which is dominated by the 1D physics, or a system which is dominated by more 2D or 3D physics. Of course, the ultimate limit is to make this tunneling so small that you can say, it's obvious, it's 1D. But it's never zero. The point is that it has to be zero compared to the temperature. Okay? And with optical lattices, you can do that very well. You just raise the optical lattice so that this tunneling is completely negligible compared to the temperature. There are solids for which this is also a good structure, and you can be in this situation. So this is another way of getting 1D systems. Okay. So whatever way you want to use, this is something that you can get. I can give you another interpretation. You could say, this is my energy, and I have to compare this term with the temperature. If the temperature is larger than this term, then I don't know if this term is present or not. So I erase it, and then I get my 1D system. So it's cheating, but that's the way it is. Okay, so this is just to sort of tell you a little bit how you can realize 1D system. I can show you a couple of examples. I don't think it's interesting to go too much at the moment into the details. This is what I just said. I mean, this is I try to put also in the slide some version of what I said. And now if you want to look at various compounds, so for the moment I won't show too many cold atoms, I'll come to that later. But here is, for example, a compound, a chemical compound, which was synthesized by this gentleman, which is Klaus Beckgard. It's called Beckgard salts. And okay, this gentleman discovered superconductivity in this material. His name is Denis Jérôme. And you see the way it works. These are molecules that are stacked on the top of each other. So there is a very good overlap of the molecular orbitals in this direction, and in this direction, and in this direction. But there is very bad molecular overlap between these things. So this is a compound which is made of these chains that I was mentioning. And you indeed can be in a regime where the tunneling here is so small compared to the temperature that you can consider that these compounds are effectively 1D, even if the crystal is 3D. The electronic motion inside the compound is effectively 3D. Nanotubes, these are tubes, yeah, sorry. Yeah. So to give you the scale, the overlap of the orbitals in this direction is of the order of 3000 Kelvin. In one of the direction, and I think it's this one, it's 100K. And in the third direction, it's 10K. So the compound goes from 1D to 2D to 3D when you change the temperature. You are absolutely correct. They move more easily in one of the direction than the other, but it's still 100K, so you can still have a regime where it's 1D. Okay, here is an effectively 1D system, which is a carbon nanotube where you got carbon atoms which have been wrapped. Now people would call it a wrapped up graphene sheet, but before this arrived before graphene. And the transverse dimensions here are so small that this is like my box, and the transverse wave function is quantized. So this is really 1D wires, if you want. And people thought about using this thing to contact very small structure, because this has angstrom size dimension in one direction and micron size dimension in the other direction. There are other realizations with semiconductors. Here is something done by Amir Yacobi in Weizmann, where it's called quantum wires. So these are semiconducting structure where he managed to do a track which contains particle which can move, which is so narrow that again the wave function is quantized enough. Okay, so there are many systems, but I don't think we should spend more time right now with all these experimental examples. We'll see some of them later. Okay, I cannot resist showing you at least one cold atom experiment. So let me go to a very old one. And this is some very old experiment in the group of Emmanuel Bloch, where again, by putting a periodic lattice by two counterpropagating lasers here, two counterpropagating lasers here, he had several tubes which are completely independent, or the tunneling here is so small that you can forget it. And then you can say, I can study the physics of the particle moving in these tubes. And these were bosons. These are bosons, not fermions. And I can decide whether they have interesting physics. So this is their n of k. So you see, it's pretty complicated. This is the momentum distribution as a function of the momentum. And okay, it doesn't look like a delta function at k equals 0. It doesn't look like anything humanly recognizable. But so we'll discuss a little bit what it should have been before we go to that. Okay. So are there questions at that stage? Is it okay? You all understand how we can get 1D systems. And now the question is, how do we solve? And so let me take first a very simple example, which is interacting bosons. I know that the school is on fermions, but if I start with fermions, everybody will explode, me included. So let's do it adiabatically by discussing the case of interacting bosons. And so I'll take an Hamiltonian for bosons, which is very simple. And again, I write it in first quantization. So it's j equal 1 to n, pj square over 2m. So I have 3 bosons. And then I put an interaction, which I can write this way. I can write G, which is the interaction strength. And then I get sum over all the pairs of bosons. And I'll put a delta function interaction. So this is Ri minus Rj, where R is the position of the particle. So I have bosons which are freely moving on a 1D system. And when 2 of them manage to be on the top of each other, Bing, they pay the price G. So this has a name. This is called the Lib and Linear Model. And this is a model that was studied in the 60s by Elliott Lib, by a technique which is known as Bethe-Ansatz, which was invented by Hans Bethe, as you can guess. And the technique consists in writing explicitly the wave function of the many-body problem. And then you've solved the problem. Well, not exactly, but that's the idea. And so there are a lot of results that came out of the Lib linear model. But it's also a little bit the Drosophila again. This is something, doing something more simple than that is impossible. If I remove the kinetic energy, okay, boring. If I remove the interaction, boring. So, and if I complicate the interaction, it's more complicated. It's hard to do simpler than a delta function interaction. So how would you solve? How would you solve? Usually what people say, they say, okay, if I was in higher dimension, I would assume that all my bosons without the interaction go into the k equals 0 state. They both condense if you want. And then, as you will see in one of the course later this week, you can write excitations on the top of this state. It's called the Bogolyubov approximation. And you study this above the condensed state. But in 1D, trust me, there is no condensed state. So it's very hard to solve. And what is worse, this is a highly wrong base. So I want... But let me just write this in second quantization, because I think it's instructive. This Hamiltonian can be rewritten as the sum of a k of epsilon k, which is k squared over 2m, times b dagger k, and I'll explain what this means, bk. And then there is a term which is g, okay, depends how you normalize, but divided by the volume, and then sum over k1, k2, k3, k4, delta k1 plus k2, k3 plus k4, and I'll explain what this means. B dagger k3, B dagger k4, bk2, bk1. So what does it mean? This is the kinetic energy. I just count, so if I destroy a boson with momentum k and I recreate it, it means I can only do it if it's present. So this is counting the number of bosons with momentum k. And each one of these bosons has an energy k squared over 2m. Okay, so that's my kinetic energy. The interaction describes the fact that 2 particles can come with momentum k1 and k2, and then they interact and they are scattered into 2 new particles with momentum k3 and k4, and essentially the momentum must be conserved. K1 plus K2 must be equal to K3 plus K4. This is a consequence of the invariance by translation of the system. And the matrix element normally should depend on the K, but because the function, the interaction is a delta function, actually the Fourier transform of a delta function is flat, which means the matrix element is just G. So this is a very simple form that you can use, which is the second quantization form, to write the same Hamiltonian that I wrote in first quantization. And the B are creation and destruction operator. And if you want, they must respect some constraint, which is they obey some very specific commutation relation, that bk1, b dagger k2 commutator is equal to delta K1, K2. And the reason for this will be explained, and it's simply because that way you ensure completely the symmetrization of the wave function for the bosons. And of course, you get the corresponding BK1, BK2 without the dagger is equal to 0. Okay. Now, this Hamiltonian is highly inconvenient because of this term, of course. And you see, terms which are quadratic like this, we know how to diagonalize. So then, usually what people do, they do some trick on this one. They do mean field, they replace 2 of this or 3 of these things by numbers, and then you get again a quadratic Hamiltonian, and then you can diagonalize. But here we have 4 particles, and we are dead. So either you're Hans Bethe and you write the wave function, or Elliott Lib and you write the wave function, or you have to find another way. But the problem is not there. The problem is that you're trying to work with the wrong basis. You know, when you do perturbation, when you do something like this, it means that at the end you want your result to resemble what you started with. Otherwise, your perturbation theory will explode in your face if it's too different. So the very idea of doing perturbation, Feynman diagrams, whatever, is that at the end, you expect that somehow what you get is practically what you started with, like 3 particles. And I told you in 1D, no individual excitation can exist. This is something we know. So trying to express this solution in terms of the individual excitations of bosons is hopeless from the start. It will be a very complicated solution. So what we need to do is to use the fact that we know that only collective excitations can exist and try to rewrite this Hamiltonian in another basis, which is the basis of collective excitations. And maybe if we do this, the Hamiltonian will become simple enough that we know how to solve it. So I'm suggesting that we try a change of variable. And this, the fancy name of this change of variable is something called bosonization. And I will tell you why it was called that way initially. But it's just a rewriting by saying, let's not work with excitation that are individual excitation. That would work for fermions in 3 dimensions, Fermi liquid. But here we expect something different. And there are various ways of doing this. So the reason why it was called bosonization, just a second, is because initially people did that for fermions. And the collective variables turn out to be bosons. So it was kind of changing basis, going from single particle fermion excitation to bosonic excitation. But you can bosonize bosons. So it should have been called collectivization, but this sounds not right. So bosonization will keep, yes. Okay, yes, you had a question. Oh no, I'm not saying it's fine in 3D, far from it. I'm just saying that in 3D, so the thing which is not the same in 3D, but there I don't want to anticipate on the course that you will get, is that in 3D, you can say I have an ordered state. So I will say that there is an average value for the operator B dagger. So in this term, which has 4 bosons operator here, I can kill out 2 of them and replace them by their average value. It's, well, it's called Bogoliubov approximation. It's a kind of Hartree-Fock approximation, but a little bit more sophisticated. And at the end of the day, you get an Hamiltonian which is still quadratic, which you can diagonalize, and which gives you very good physical description of the properties of the system, because this exists. No. And the reason it does not exist, which I didn't justify to you at all, is the fact that in 1D, the quantum fluctuations are stronger and prevent the existence of this average. You know that, for example, if you do phase transitions, the Ising model has a phase transition in D equal 2, has a phase transition in D equal 3, D equal 4, but in D equal 1, it has no phase transition and no ordered state, because thermal fluctuations are strong enough to prevent the formation of an ordered state, a spontaneous symmetry breaking. It's the same with quantum fluctuations. quantum fluctuations will prevent formation of the spontaneous symmetry breaking if the dimension is too low and 1D is too low. 1D is one spatial plus one time direction, so it's like two classical dimensions. And it's a model with a continuous symmetry, which is the phase symmetry. So it's like XY model in 2 dimensions. It has no ordered state. So this does not exist, meaning this is 0. It exists, but it is 0. And therefore, you cannot expand around it. That's the point. Are there other questions? It's okay? Okay, so we have to find a way around it. And another thing you could try to do is to do an hydrodynamic approximation. Usually, if you say I have particles which have a certain spacing A, I can do a kind of hydrodynamic approximation. When you do this, you lose everything below the scale A, the scale of the particle distance. So here we would like to be able to do better than that. And so let me describe a method which was invented by Duncan Haldane. So this is a very beautiful paper. This is a PRL by Duncan Haldane. You have the reference in the reference that I gave. I can find the reference and give it to you explicitly. Of course, the method was already known in a different form before. It was developed in the 60s and the 70s. But the way he does it is extremely beautiful and extremely generic. The other method, the other way to implement the methods were more specifically focused to fermions. So I will try to give you the method. So for that, let's try to look at the density of particles. So the density of particle I can write in first quantization. This is an operator. This is delta of x minus xj, where xj is the operator measuring the position of the jth particle. This is a set of delta functions as a function of x at the position where the particles are located. This is a very unpleasant operator. This is a very discontinuous operator. This is 0, 0, 0, 0, infinity, 0, 0, 0, 0, infinity, 0, 0. So if I want to do a smooth approximation, it's not very, very easy. Okay. Now, let's imagine that I have a crystal of bosons. Well, you know, free bosons, it's far from being a crystal, but let's imagine I have a crystal. Then if I had a crystal of bosons, then I would have bosons in a regular set of positions. And now I could imagine saying, oh, I can describe the position of the bosons by small deviations from this perfect crystal. So I would say I put some U, and it tells me how the particles, this one has moved backward, for example, and whatever. So I could imagine introducing for each boson a certain field, which is the displacement Uj, which tells me how I deviate from this crystal. This is what you would do for classical particles. You all went through this in your basic solid state course, like doing phonons and whatever. The point is that still very complicated to write this Hamiltonian. This would work in any dimension, provided you get the crystal. So we'll do it in a slightly different way. So the idea is in one dimension, actually, what I can do, which I cannot do in higher dimension, I can label the particle in a unique way. I can start here, say this is particle 1. Now you will tell, well, look, they are indiscernible, so how can you label them in a unique way? I don't care. If they cross, the one on the left still keeps the smallest number. The one on the right keeps the largest number. They are indiscernible, so I don't care. Still a unique way. If I have trajectories that cross, I can always say this is one of the trajectory, this is the other one of the trajectories. So I don't care. But I can label them in a unique way. So let me rewrite the density in a slightly different way. I will introduce some object, which I will call phi L of x, which is a function, which is actually an operator. And I want this phi L of x to be equal to an integer, actually 2 pi times an integer, but that's a detail, where I have a particle. So I define the position of the particle with the fact that phi L of x is equal to 2 pi times an integer. And this gives me the position of a particle. So let me give you an example, because this sounds a little bit very abstract, but actually it's not. Let me take the function phi L of x, which is this straight line. Well, when this is 1, I get a particle here. When this is 2, I get a particle. When this is 3, I get a particle. So if I choose phi L of x like this, what did I do? I created my crystal. Okay? And the slope controls the density of the particles. So phi L of x is 2 pi or pi rho 0 x, means I have a particle with a certain average. But you see that now if I distort phi L of x, so instead of doing it that way, I do it that way, for example. Now, this particle has moved here. This particle, which was here, has now, where is it? It has now moved here. And this particle has now moved there. So by using this phi L of x, I can put the particle a little bit where I want. But this is a smooth function. So for this one, I can do an hydrodynamic approximation. Not for the density, but for this field, I can do an hydrodynamic approximation because it's smooth. So I will use this field in a way to rewrite the density as a function of this field, knowing that my particle forming a perfect crystal means this field is totally straight. And my particle being all over the place means this field will wiggle a little bit, change a little bit, but not too much. Okay? Because if this particle was going very far, it's not my first particle anymore. It's become my 25 particle, but I don't care. I number always from left to right. So they cannot move by more than A. So this is a weird trick. You know, Duncan Halley didn't get the Nobel Prize for that, but he could have. So I'm just saying this is a nice, very nice idea. So I will give you the result. I let you do it as an exercise tomorrow. If you have not managed to do it, we can do it on the board. But you can check that you can rewrite the density. So of course I can rewrite the density very easily. It's rho of x is equal to the sum over p, let's say an integer of delta of phi L of x minus 2 pi times p. Actually, it's not correct because there is a Jacobian in the transformation, and I should put it, and the Jacobian of the transformation is just the derivative, the gradient of phi L of x. This is easy to check. So it's an exact statement. Now I can rewrite this by using the fact that I can write a delta function as an exponential, blah, blah, blah. This is a Dirac-Coombe. I can write a Dirac-Coombe, blah, blah, blah. Let me cut a long story short. Rho of x can be written let me reparameterize phi L of x because it's convenient, as 2 pi rho 0 x minus something, and I don't want to cheat you on the coefficients, 2 phi of x. Why this? Because if this is a straight line, I get my crystal. So these are the deviations from the crystal. So I want the slope, which has the correct density, and then these are the deviations. If you do this, then this is rho 0 minus 1 over pi grad phi times sum over p of exponential of I 2p times pi rho 0 x minus 2 phi of x. Now, this is a very nice formula, and you could say you're completely nuts. So p is an integer, positive or negative. You had a very simple looking operator, and you wrote it in this very complicated way. So why did you do that? The point is that I don't know how to take the smooth limit of this very nice looking operator with the delta functions. But there, I can say phi is the smooth field, which will vary very slowly at the distance of interparticle distance. So that's my collective variable. Now, let me give you just the physical justification of this, and then we'll stop to take questions, because then I'll continue tomorrow. Look at this. This is a beautiful formula that do a Fourier transform in the way of the density. Let me take here the term p equals 0 in the sum. If I take the term p equals 0, then I have the density, rho of x, which is equal to rho 0 minus 1 over pi grad phi. That's exactly what you would expect in a crystal if you were doing displacements that are bringing, for example, the particles closer to the center. Actually, if I have done this, I've increased the density around the center, like this. And I can do it smoothly. Phi varies very slowly at the scale of the lattice spacing. This is the elasticity term. This is the hydrodynamic term. This is what you learned when you did displacement phonons or whatever. You just move your particles slightly away by a displacement. So this was the U I was talking before. Phi is essentially U. And here I brought density, but the modification is very slow at the scale of the lattice spacing. So actually I drew it with one lattice spacing. I should have made 25 of them. But that's not the only modification I can do. Let me now take p equal 1. If I take p equal 1, and let me throw away the gradient term, the density is